Today we are looking at reflections, a type of transformation. We're going to look, oops, sorry about that. We're going to look at them and a couple rules and patterns that we see when working with reflections. Okay, so this first part of your notes says that we're going to reflect this triangle across the y-axis. Well, here's the y-axis. And we're going to reflect it. Well, we find the three vertices, and for vertical and horizontal lines it's fairly easy because all we really need to do is count the distance from the line that we're reflecting across. For instance, P is 1, 2, 3 units away from this line right here. So our new point that's being reflected is going to be right there. And I would use red to show that. H is 5 units from the edge. 1, 2, 3, 4, 5. So the new point is going to be 5 units. So we've reflected it, H, to this point. And Q is 4 units to the y-axis, so the new point will be 4 units from the y-axis. And we have Q. So we connect these dots, and what we have now is the reflection across the y-axis. Okay, now we're going to reflect across the line y equals -1. Well, there's probably some confusion as to what that line looks like. Remember, if it's y equals, it's a horizontal line. If it's x equals, we end up with a vertical line. This is y equals -1, which means the line we're reflecting across crosses the y-axis at -1 and is horizontal. Okay, we follow the same rules. We're going to go ahead and find our vertices. P is 2 units away from my line, so the new point is going to be 2 units away from that line. H is 4 units. 1, 2, 3, 4. So my new one is 1, 2, 3, 4. And Q is 5, so 1, 2, 3, 4. It's actually off the grid here. We connect the dots of my vertices, and what we should have is the figure reflected across that line y equals -1. Well, you might notice in these two examples we had rigid motion. So as far as the question here, is it isometric? Remember, isometric is just another way of saying, is there rigid motion? Was there no change in size or shape? So if there is no change, then it is isometric. And yes, it does have rigid motion. One thing to think about with our reflection, all we're doing really is we are flipping it. Okay, so we flip when we have a reflection. You know, in class we talked a little bit about it as far as when you look at your shirt in a mirror, when you see your reflection in the mirror, the words are printed the other direction. You see the words on shirts, so yes, they are flipped just like you would see letters flipped in a mirror. Okay, the next one I would like to first bring to your attention this right here. We're going to fill out this little chart first before we begin. When we reflect across the x-axis, if we're on a coordinate plane, then we keep the x the same, but whatever our y-coordinate is, we make it negative. Sorry about that, I meant to write -y. Let me rewrite that. X -y. Okay, when we reflect across the y-axis, well, my x now is negative and we keep the y. So that's when we reflect across the y-axis. In a minute we're going to talk about the y equals x, so let's just fill this chart in. We make our y-coordinate my x-coordinate and my x-coordinate my y-coordinate. And when I have y equals -x, that's the line I'm reflecting across. Then I make my y my x, but I also change the sign. And I make my x my y, and again I also change the sign. So using these notes right here, let's look at this example. I'm reflecting on number 1 across the y-axis. So according to our notes, when I reflect across the y-axis, my coordinates are, I change the sign of my x and I keep the y the same. So what we're going to do is we're going to find the points of the vertices and then find the new points, the new coordinates of my vertices, and plot them as the reflection. So we'll start with this point on bottom here. That would be 1, 2, 3, negative 3, up 1, 1. So my new point would be I change the sign of my negative 3 to get through positive 3, and my y would stay the same. So the reflection would be right here. Okay, let's find this point right here. That would be negative 1, 2. So my new point would be, instead of negative 1, again I'm changing the sign of my x to be positive 1, and my y stays the same. So that would be 1, 2. Okay, let's change this. Let's find the coordinates for the point above that. That would be negative 1, up 1, 2, 3, 4. So negative 1, 4. To change those signs, I change the negative 1 to a positive 1, and I keep the 4 the same. So those points would be, that point would be up here. You're probably noticing a pattern that we could just count across like we did in our first examples. We can when we're dealing with vertical and horizontal lines. It's a little bit easier. This next point would be negative 2, 1, 2, 3, 4, 5, 5. So my new point is going to be positive 2, 5, which would be right here. Okay, we continue doing that with all of these vertices, or else, I'm going to do this next one in blue, but if I'm looking for this point, we can also say it is 1, 2, 3 units from the y-axis, so it's going to be reflected 1, 2, 3 units, and it'll be there. This point would be 4 units, so it would be here. This point would be reflected 4 units, so we'd be here. This point would be here. And this point is 3 units away, so it would be here. Connect the dots. So we did that both using our rules for reflections, but at the same time we can make it a little easier just by counting. For instance, number 2. My rule says in that chart below that if I reflect across the x-axis, my x-coordinate stays the same, and I change the sign of my y-coordinate. Well, if I find the ordered pair for this point, that would be negative 7, 2. Well, according to my rule, x stays the same, y becomes flipped, so that would become negative 7, 2 would become negative 2. And that would be right here. Again, we could have just said 2 points, 2 units away from the x-axis. So now if it lies on the actual axis that we're reflecting across, well, my new point is going to be the same point. So that point stays there. This point is 3 units from the x-axis, so it's going to be reflected 3 units from the x-axis. And the last point is 2 units from the x-axis, so we're going to be right there. Connect the dots, and we should have our quadrilateral reflected across the x-axis. Alright, right here. Now this is where it comes in handy having these rules for reflections. According to these rules, it says that for y equals x, we flip the y, the x, and the y coordinates. So we find all the points, and then we find the points by reflecting them. So here we have -3, -1. Here we have -3, 1. Here we have -4, 1. -4, 2. -2, 3. 0, 2. And the last point would be -2, 2. Okay, so those are the ordered pairs for all those points. Well, I'm going to make a list of the opposites. Starting with 0, 2, that one's going to be 2, 0, because remember my rule says that I flip the 2 around. So that's going to be 2, 0 right here. My next point, -3, -1, is going to become -1, -3, because I flipped it. So that's going to be right here. Connect those dots. Now I'm going to do this point, which -3, 1, I'm going to flip those and get 1, -3, which is going to be right here. And I'm going in order so I can connect it and so I know which order to connect it. A -4, 1 is going to become 1, -4. Notice the signs all stay the same. I just flip their position. -4, 2 is going to become 2, -4. Just flipping them again, which is right here. Next up is -2, 2. So flip those. I'm going to end up with 2, -2. 2, connect the dots. -2, 3 is going to become 3, -2. And we're back to the beginning, so I connect the dot. And you see that what we have is that image has been reflected across that line, y equals x. All right. Number 4. Now this one doesn't have an x or y axis, so another way we could do this, besides using the rules for reflection, we could see that we're going to reflect each of these 4 points across this line. Well, our distance, shortest distance in a perpendicular direction would take us through this. So we could count, notice this is 1.5 units. So this distance right here is also 1.5. Again, it would have to be a perpendicular line, which we would use. We could plot this point. This would be 1 point. Some people understand it, some people get confused by this. Remember, we're drawing a perpendicular line which has an opposite slope. So we're looking at this, which has a distance of 2.5, so we would be right here. Notice we have 1, 2.5. So we have a 1/2, 1, 2, that makes 2.5. So that would be the reflection of those lines. Now, another thing you can do for these problems is you can draw your own XY coordinates if you struggle with diagonal lines and reflecting points across them. For instance, we could make this my y-axis. We could make this my x-axis, and now what we have, this dotted line, we're reflecting across the y equals x line, which the rule for that is y becomes my x and x becomes my y. We could then find each ordered pair and do just like we did before. The points would be -2, 3, 0, 3. negative 2, negative 3, and 0, negative 3. If we write those new points, well, 0, 3 is going to become 3, 0, which would be right here. Negative 2, 3 is going to become 3, negative 2, and again, I'm just changing these based off my rule. 0, negative 3 is going to become negative 3, 0. And negative 2, negative 3 is going to become negative 3, negative 2. If I draw that line and connect the dots, there we have the reflection across that line, y equals x. Okay, number 5. Again, they're easy when they're horizontal and vertical because we can just count the points. If the vertices lie on the axis, they stay there. So these two on the dotted line will stay there. This point is 1 over, so we're just going to move it 1 over. This point is 1 over, so it's going to be 1 over. This other point is 4 over, so it's going to be 4 over. And again, 4 over. So there we have it. We connect the dots, and we have reflected that image across that vertical line. Okay, number 6. If we were to reflect, these points are going to stay right here because they're on that line of reflection. This point, it is 2 units across, so it's going to be reflected to this point. This vertex is going to be reflected 2 across, and it's this one. As we do this, we notice that it's going to reflect exactly over itself. And if we connect those dots, we end up with the same shape in the same place. Okay? So what we have here is a line of symmetry, which leads us to our next page of notes. When we have, looking at a few definitions and questions on the next page of notes, we see that the formal term for a line that an object is reflected across, like that M was, is the axis of symmetry. And symmetry exists if a figure can be mapped onto itself by rigid motion, meaning we don't change the shape or size, mapped onto itself. That M was mapped onto itself. Now that example we had was line symmetry, and it exists if a figure can be mapped onto itself by a reflection, which we did do. And below are just some examples of line symmetry. How many lines of symmetry does a circle have? Well, if we had a circle, imagine that's a perfect circle, not an oval. There's a line of symmetry. There's a line of symmetry. There's a line of symmetry. And in theory, we actually could have an infinite number of lines of symmetry because we could always draw another line of symmetry in any place on the circle. Okay, those are the notes for reflections. Hope you find this helpful. That's it.